Okay, so today, if you look on the syllabus, what we've been talking about is standard flows, and this is the last lecture on standard flows. So I'll summarize a little bit, and we're going to finish up with an example, and that'll finish up this chapter, and then we'll move on next week to material functions. So that'll be a new topic. I've handed back the homework, so with the solution. So if you have any questions about that, I'll take them after class. I'll take them in office hours on Monday as you prepare for the exam, which is on Tuesday. So that'll be good. So let me just summarize what we're doing here. This was the beginning of the lecture for standard flows. And I motivated this by saying we're trying to determine between Newtonian and non-Newtonian fluids. And we're going to do it by imposing various flows. Depicted on this slide are a shear flow and a uniaxial elongational type of a flow. So overall, we define two flows. The simple shear flow, which is defined by its velocity field. And as I pointed out before, that's different from the idea of knowing the constitutive equation, the Newtonian fluid, and solving for a velocity field. Here we're choosing ways to poke and prod at liquids, and we're going to poke and prod at them this way, by putting them between two parallel plates and moving the top plate fast, and assuming that the velocity profile we produce is this one, and then we're going to interpret the stresses that are produced. So towards the end of the lecture last time, we talked about the stresses that are produced in shear flow. There is one shear stress, which is related to the force that it takes to move this top plate. And there are three normal forces. One, the force that it takes to keep this plate from going up. Another force, a normal force on a one surface in the one direction. And one I can't draw, which is a three surface on the three direction. These are normal forces, perpendicular forces. Now, how are these normal forces different from pressures? Pressure would be the same on this surface, the top surface. Pressure would be the same on, at let's say some point. Pressure would be the same on a surface that's a one surface, or a surface on a two surface, or if I drew a line into the plane, the three surface. The pressure is the same on all three surfaces. But those normal forces that I'm talking about, they're not the same. They're still anisotropic forces. They are not isotropic pressure. So at a given point on three different surfaces you might draw through that, the normal forces may be different for non-Newtonian fluids. And that's very different from Newtonian fluids. So we need to be able to evaluate those pressures, those forces, excuse me, those normal forces. The shear force we need to evaluate, and the normal. So in these devices, which you've seen before, we can always measure shear force very easily, and many of them are designed only to measure shear force. This cone and plate, I've said before, is a very popular one. This one allows you to measure first normal stress difference, because you can measure the thrust that it takes to keep this top cone from going up. So this one is capable of measuring normal and shear forces. This one is only capable, and this one are only capable of measuring the shear forces. The second flow we have talked about is elongational flow. There are three types: uniaxial, biaxial, and planar. And in this flow, there were two forces that are important, two stress differences. One, the stress difference between one and the two directions. So that typically in this flow, you would have some kind of a column of fluid like this that you're stretching. Let's see if I have them here. Here we go. A column of fluid. And we know the normal force on the sides, it's atmospheric. And we know the force that it's taking to pull it apart. All right? And the difference between this force and this one will give us that one primary normal stress difference. And because this flow is symmetric, there's actually only one stress difference we need for this flow. So we talked about the forms of those flows, and I also defined these other two flows, the biaxial and the uniaxial. Excuse me, biaxial and the planar elongational. But then I also discussed, and this is an important point, the idea of why we chose these flows, and I gave the answer why we chose these flows. We chose them because steady flow, simple flow, simplifies the number of stress components we have to measure. And so the simplicity of these flows is really due to their symmetry, and that's what I finished up the discussion with last time. So the stress tensor is in general 9 components. Symmetry of the stress tensor reduces it to 6. Symmetry of the flow itself, which means in the case of shear flow, having an axis here in the center, that if I rotated this flow by 90 degrees, I would get the same flow. This point would rotate up to that location, this point would rotate to that one, and you'd have the same flow. And that symmetry we can show, and we did show mathematically, implies that the 1, 3, 3, 1, 2, 3, 3, 2 components of the stress tensor are 0. Very, very handy. Okay? So we reduce the number of stress components, again saying absolutely nothing about the constitutive response of this material, but we know without saying a word that it will only have 3 normal stresses and 1 shear stress. For elongational flow, because in this case, we can rotate it along this axis again, and this point comes down here, and this point goes up there, and you get the same flow. But you can rotate around the 2 direction, or the 1 direction, or the 3 direction. The flow is symmetric in 3 axes, which leads to all the shear components going to 0. So this one is even simpler, even more symmetric, and we only have 3 stress components. Now, towards the end of lecture, I got to a slightly harder concept, which maybe I'll review a little more thoroughly just now, which is the idea of stress differences versus stress components in general. So we're back to the total stress tensor, which is actually the stress tensor we measure. When we put some sort of a device up against, let's say I have a flow, and I could maybe make a little port here and screw a transducer in and measure pressure, okay? This transducer, usually this would be a normal force type transducer, it can measure a little bit of thrust. If there's a little bit of thrust, it'll deflect the gauge or deflect the meter in some way and tell you there's been a little bit of thrust. What it will measure is a stress component that is a normal stress component. Pi, in this case, if it were shear flow, this is stress on a 2 surface. This is the 1 direction, this is a 2. Stress on a 2 surface, a surface whose unit normal is E2, in the E2 direction. Okay, it can't distinguish between the pressure and the extra stress. They both will be the same thing. They're both normal forces at that location. So we can't distinguish between these 2 stresses. If we had a way of measuring pressure independently, we could subtract it off, but for incompressible fluids, there's no independent way of measuring P. If it's a compressible fluid, we can measure P. PV equals nRT, or some more complicated equation of state. We measure T, we measure number of moles, we measure volume, we deduce the pressure, we subtract it from the measurement, we get tau22, everything's fine. But that comes about because pressure and volume interact. The fluid responds to pressures with density changes, with volume changes. It's compressible. When it's incompressible, you can change the volume all you like, you can change the pressure all you like, the volume doesn't change, and you can't do that trick anymore. And that's where we get this conclusion. For incompressible fluids, there's no independent way of measuring the pressure. The good news is we don't really need to measure the pressure. For flows, all we care about are gradients in pressure. And so when we take the differences that result in getting this kind of gradient, the pressure drops out of the measurement. So for instance, if we want to measure the first normal stress difference in shear flow, we can measure pi 11, pi 22, subtract them, and the pressure drops out, and we get tau 11 minus tau 22. If we find a way to measure the pi 22 and pi 33, we can subtract them, and the pressure drops out, and you get this second normal stress difference. So we will always, in the case of normal stresses, be talking about differences, and shear stresses we'll talk about bare. Remember, it's not a problem in shear because there's no pressure. See, there's no pressure component here. The isotropic part, the pressure only affects the diagonal, the normal stress components. This, I think, is a little hard to grasp at first, but not to worry. The take-home message is that the stress quantities that we will be measuring are shear stress, first normal stress difference, second normal stress difference, and in elongational flow, in uniaxial elongational flow, we'll be measuring a stress difference related to the flow direction stress and a stress difference related to the neutral directions, which will often be 0. Okay, so there's just one more topic I want to cover in this standard flow chapter, and that's a little example that helps us to get some sense of what these things are, the shear normal stresses. Because I think it makes sense in an elongational flow. I don't have a picture, but if we, in an elongational flow, we certainly expect there to be these kind of stresses. And in a shear flow, we expect there to be shear stresses. But until we study rheology, we don't usually talk about these normal stress effects. These are unique to polymers and other complex materials, but mostly polymers. So the classic first normal stress effect is rod climbing. Okay, so this we saw in the video. In the video, he showed a stirring machine in a similar beaker to this, and as you turn it, the fluid climbs up. In fact, his first example of rod climbing was his wife's favorite recipe. You remember his little joke there? That when you have glycerin in a bowl and put it in a mix master, it doesn't climb. But if you put a flour-water mixture, flour is a polymer, it climbs very nicely up into the motor and makes an enormous mess. This is a normal stress effect. Okay? Newtonian fluids do not do it. Here's an example of glycerin. Glycerin, if you stir this rod like crazy, will dimple a little bit in the middle due to inertia. And you can mathematically see where that comes from. That comes from that term that you saw in the homework. On the left-hand side of the equation of motion, you saw a term, v squared theta over r. Okay, that inertia term on the left-hand side causes that vortex in stirring. Okay, that's an inertia effect. That's the left-hand side of the Navier-Stokes equations. Where the density is, that's where the inertia is. Where the viscosity is, that's where the viscous contributions are. So for Newtonian fluids, when you stir them, it's not the viscosity that causes that dimpling. It's the left-hand side in a flow with a theta velocity, just like the one you did in the homework, tangential annular flow. You can get this inertial effect. You can predict that there will be a pressure, tendency for the pressure to draw down the top surface due to this component on the left. What about this mess? Okay, this happens, by the way. I can make a demo of this, but it would take me a while to make that polymer because you need a nice long polymer. But if I would make a polyisobutylene solution, or even polyacrylamide solution of a sufficient viscosity, I could get that thing to crawl up the top by just sort of turning it at this speed. Just turn it very slightly like this. In fact, you can just sort of crank it up like a slow crank, and it'll just come up, up, up the rod. Nothing like what I have to do to even get a coffee cup to kind of dimple down. That's inertia. You need some speed for that. This is totally not inertia. This is not about speed. You just barely turn it and the stuff comes up. You stop turning and the stuff goes down. Okay? It's a very, very dramatic effect. If we turn back to the equation of motion, what causes this to occur? And that's the question I want to address today. I want to ask, what in this Cauchy momentum equation, okay, so this is the one for non-Newtonian fluids with the minus del dot tau. What causes rod climbing? That's my question. That's what I want to go through this example because it shows the power of these kind of microscopic analyses. Now, I'll tell you that the complete derivation that I'm going to do is already on the web. If you go to the extra handouts page of our web page, you can download this handout that I have that I'm working from, and all the details are there. So it's good to copy things down, but if you miss anything, it's available on the web already. So that's the example I'm going to do. Now, one more thing to discuss is the question of, so I'll give you the punchline. The punchline is, it comes about because of the typical values of the first normal stress difference. This is a first normal stress difference effect in a flow. The second normal stress difference is even harder to visualize, okay, this second normal stress difference. In shear flow, the first normal stress difference is that tendency for the plates to separate, and it's very real. The second normal stress difference is the difference between tau 2,2, so that's this top surface, tau 2,2, and tau 3,3, which is a surface, the force on a surface in the neutral direction. Okay? Not at all clear that there should be forces somehow in that neutral direction of shear flow. I'm shearing this way, and I'm saying that there's either going to be a suction or a pressure on this surface. The way that was finally definitively determined that there were second normal stress differences, because it had been hypothesized until even 30 years ago that maybe it's zero, it was definitively shown with the experiment I have on this next slide. This was work done by Roger Tanner, and this is how it appears in his book. He took a trough, okay, so just a square channel trough of liquid. And it's not a meniscus effect. In the trough, when it's level, you have this flat surface in the trough. And he's got these little measurement points on the top, and they're reflecting in the liquid. And you can see that it's a flat interface. If you look really close, there might be a little meniscus effect on the edges, but it's a flat interface. If you then tilt the trough, and now it's flowing in a shear flow, what does it do? It bows. Okay, so this surface is bowing upward, okay, just because of this flow. And that's the second normal stress effect. So you tilt it, it doesn't just flow down with a level surface. Newtonian fluids flow down with a level surface. Certain non-Newtonian fluids with a large second normal stress difference will bow upward in this flow. So let's do the example. Here's my starting question. Can the equation of motion, the Cauchy momentum equation, predict rod climbing? All right. For typical values of N1 and N2, typical values of N1 and N2 are that N1 is typically negative and much bigger than N2. N2 is typically positive and about 1/10 the size, 1/10 the size of N1. So let's give it a try. So all I'm going to do is start with this Cauchy momentum equation and try to simplify it for the flow that I have on this slide. And so this is going to look like I'm trying to solve for the velocity field, but all I'm going to look for is what is the effect of these quantities on the pressure on the top surface. If the pressure tends to be such that it would be larger near the central axis and smaller near the outside, that would be rod climbing. If the pressure tends to be larger near the outside and smaller near the inside, that would be the vortex flow of a Newtonian fluid. Okay? So here it is. Now we're going to simplify it. We're going to be in this cup and bob geometry, and we're going to turn the inner cylinder just like we did in the homework. And we're going to turn the inner cylinder at a steady state. And we know already that this is not 0, right? Because v dot del v is 0 when the streamlines are perfectly straight. And this is certainly not one of those cases. And the homework is fresh in our minds. We know that that v squared over r term comes into play. So we're going to have to simplify this term. For the pressure term, we're going to assume theta symmetry. So I'll assume steady state. I'm going to assume theta symmetry. So that will allow me to take care of all the d by d theta derivatives that appear everywhere. And I'm going to neglect variations in z. This is usually like my tall cylinder assumption. So starting with the term on the left, this one, v dot del v, we need to get these terms from the tables because we're in cylindrical geometry. So I've got the tables out in front of me. Cylindrical coordinate system. And I want to direct your attention to this entry here. This is the v dot del v entry. Okay? And so I don't have to copy it all down. We'll just look at this together. We know that the velocity is only in the theta direction, right? It's only in the theta direction for this flow. So that means that the VR is 0. VR is 0. There's a v theta over r. VR is 0. V theta, this term, there's a ur there, so that goes to 0. This term, v theta doesn't vary with theta, so that one goes out. VR is 0. No VZ. No VR. No VZ. No VZ. So v dot del v simplifies quite a bit. This top one, I'm just going to sneak this up there a little bit. There we go. The top one, there, that u theta is a v theta. And that v theta over r becomes this v squared theta over r term that you remember from the homework. This one's 0. This one is 0. That's 0. That's 0. Everything is 0 in the second line. VZ, VZ, VZ is 0 in the third. So now we have v dot del v is the same one that we had from the homework. V squared over r minus in the r theta z component. Now we go to the second term, which is the pressure. We know how to do pressure. That's very simple. Minus grad p is minus dp dr minus 1 over r d by d theta of p and minus dp dz. And because we neglect theta and z variations, we only have r variations. So the left-hand side is this times rho, and then this is the first term on the right-hand side. Gravity is irrelevant, so we'll neglect gravity. And that leaves us one more term, del dot tau, which is going to be an important one. So for the del dot tau term, I'll actually copy it all down because that's the meatiest one, the one where we have to think about it the most. And I'm going to copy it down on a gigantic sheet here. So this is a vector, del dot tau equals 1 over r d by dr of r tau r r plus 1 over r d by d theta of tau theta r plus d by dz of tau zr minus tau theta theta over r. That's all the r component of del dot tau. The theta component of del dot tau is 1 over r squared d by dr r squared tau r theta plus 1 over r d by d theta tau theta theta plus d by dz of tau z theta plus tau theta r minus tau r theta over r. So 1, 2, 3, 4 terms to the theta component. And then finally the z component, 1 over r d by dr of r tau r z plus 1 over r d by d theta of tau theta z plus d by dz of tau zz. Now, can you suggest any of these terms that I can get rid of? All the d by d thetas, correct? Thank you. Right. We also assumed that it was a very long tube and that there would be no z variation. So those go too. So we didn't need to know much about the stresses yet, because all we are asking questions about is how the stresses vary in space. Okay, so these three have something to do with r variations of tau rr, tau r theta, and tau rz. Okay, so I'm not going to ask questions about the stresses, but just about the variation. When we are expecting r variations, we're asking whether the pressure varies as a function of r. Is it smaller in the center compared to the edge, or larger at the center, rod climbing, compared to the edges? So these are the three terms we expect to be important. And then we have these mystery terms here. This one, if I were going to get rid of this, I'd have to know something about tau theta theta, about which I know nothing, so I'm not going to say anything at the moment. But this one I can do something about. Do you see what's going on here?
Shouldn't those be the same?
Yes, for a symmetric stress tensor, those are the same. So this stress tensor in the book is written in the generalist case, most general case, as if it were asymmetric stress tensor possibly. But as long as the stress tensor is symmetric, that one goes too. Okay, so all we've done is take out theta dependence, R dependence, and stress symmetry, and we've got just these two terms in the R component, one term in the theta and one in the Z. So now let's put it all together. Here's my equation of motion. Oops, equation of motion. Sometimes I write EOM, equation of motion, minus rho v theta squared over r, 0, 0. That's the left-hand side, equals minus dp dr, 0, 0. That's the pressure term. And then minus this interesting term, 1 over r d by dr of r tau rr minus tau theta theta over r. 1 over r squared d by dr of tau r theta r squared. 1 over r d by dr of r tau rz. It still looks kind of complicated. I would be intimidated to solve this problem, but we're not trying to solve it. We're looking at it, and we're seeing what the different terms mean. And we're saved about this term here, the R component and the theta and the Z components aren't telling us anything about the pressure variation in the R direction, so we don't even need to ask any questions about these two terms. That's telling us about the flow, but we're not asking about the flow. We're asking about the pressure. We're asking, as I turn this rod, will the pressure variation go up and then down, or down and then up? This would be the inertial effect. This would be rod climbing. So I need to know how things vary with R. So I'll copy down the R component. That's the one I care about. Minus rho v theta squared R equals minus dp dr minus 1 over r d by dr of r tau rr minus tau theta theta over r. All right, and now the only additional information I am going to have about stresses is about this N1 and N2. Okay, we know that N1 is typically negative, and N2 is, have I got that backwards? No, I've got that right. Is positive and small. Now, what is N1? N1 is tau 11 minus tau 22. N2 is tau 22 minus tau 33. Where? 1 is the flow direction. So what direction is that? What's the direction of the flow? Theta. 2 equals the gradient direction. That's the direction in which the flow varies. What direction is that? R. Right? The flow's going around like this, and it varies with R. 3 is the neutral direction. These are the definitions for shear flow. And the neutral direction is Z. Okay, so tau 11 is tau theta theta. Tau 22 is tau RR. Tau 22 is tau RR. Tau 33 is tau ZZ. So looking back at our equation, we've got a tau RR and a tau theta theta. But they're kind of mixed up a little bit. So let's multiply out. This is an unusual choice, actually. Let's multiply out this derivative to make it, I can tell there's going to be a product rule here. Maybe I can combine these two variables somehow if I'm lucky, and I'll get a tau theta theta minus a tau RR in there somewhere. Okay, so let's try that. Minus rho v theta squared over r equals minus, I got lots of minuses. I should have multiplied through. Oh well, next time. dp dr minus 1 over r times the first times the derivative of the second plus the second times the derivative of the first, which is 1. Multiplying that out and get rid of those minus signs. Rho v squared theta over r equals plus dp dr plus d tau rr dr plus tau rr over r minus tau theta theta over r. So our wish has come true that N1, if I go back here, N1 is tau theta theta minus tau RR. So we got something going right here. This is equal to minus tau theta theta minus tau RR over R. So that's minus N1 over R. This is interesting, but actually it's kind of our saving grace again, because this question I'm asking about the flow, I'm saying I have a rod in a vessel and I'm turning it, and I'm asking about the pressure variation as if I put a lid on the top. Okay, if I put a lid on the top and measure the pressure all along the surface, if I put my pressure transducer on there, I said I would not measure P, right? I said I would measure pi. Okay, so what I'm actually going to measure right here is pi. Which one? Okay, the one direction is theta. What surface is this? A surface of constant what? Z. So this is a curve of a constant Z. Its unit normal is EZ. So this is stress on a Z surface in the Z direction. We don't have any Z's in our problem. But if I subtract and add a tau ZZ over R, one of the terms will combine with this and give me a derivative of n2, and one of the terms will combine with this and give me the pi that I'm looking for. Tricky. I didn't come up with it, but brilliant. Very brilliant. Okay, so what I'm going to do is I'm going to add and subtract pi zz over r. To the right-hand side of this equation. So let's do it. Okay. Rho v theta squared over r equals dp dr plus pi zz d pi dz dr plus tau rr dr minus d pi, excuse me. I want to add and subtract not pi but tau. My mistake, because I'm going to turn it into pi. Doing it correctly now, second time's the charm. Rho v theta squared over r equals dp dr plus partial with respect to r of tau zz plus the term that's there, d by dr of tau rr, minus the term I just added in so that I've done nothing, plus this big mess was minus n1 over r. So I've added the derivative of tau zz and I've subtracted it, so I've done nothing. This term was there before. This term I transformed into minus n1 over r the last time. So now I recognize this as d by dr of the thing I can measure, pi rr. And this, going back to my previous slide, n2 is tau rr minus tau zz. Tau rr minus tau zz, tau rr minus tau zz. This is d by dr of n2. Rho v theta squared over r equals d by dr of pi rr plus d by dr of n2 minus n1 over r. Or solving for the pressure, which is the one I really want, the way pressure changes in the r direction, exactly the question I was looking for. The way the total pressure, the total normal force, changes in the r direction is equal to rho v theta squared over r, a most definitely positive quantity. Because of that square, it's unambiguously positive. Minus partial, the rate at which n2 changes in the r direction. Now, I don't know much about n2, and I certainly don't know how it varies in the r direction, so that's a slightly problematic term, but it is small. We do know that n2 itself is small. Plus n2 over n1 over r. So, what does it tell me? If I plot, starting in the center and going to the edge, here's my rod. Here's pressure. Here's total normal force as a function of radius. This will be the edge. This will be 0. And this will be the inner edge. Let's say kappa r, using the same nomenclature from the homework. Is it a decreasing function or an increasing function? This is telling us what its slope is. Okay, if the slope is positive, it's an increasing function, right? If the slope is negative, it's a decreasing function. This is positive. This is small. And this is negative. So for a Newtonian fluid, both of these are 0. Is the slope positive or negative? Positive, and so it does this, and is that what you're expecting? That's the dimple in the center for a Newtonian fluid. For a non-Newtonian fluid, this term is still positive. But for some non-Newtonian fluids, this term is very large and negative. If it's large enough, if it's polyethylene oxide, if it's polyisobutylene, the inertia is irrelevant, and the thing has a negative slope. There's a net upward pressure on the lid, which indicates that if I didn't enforce the flow to be theta direction, which I have in my solution, but if I didn't enforce it, there would be a tendency for it to crawl up the rod. Okay? So when N1 is negative and large, I get this. When N1 and N2 are both 0, I get the inertial effect. And it's positive. How does N2 vary with R? Like I said, I can barely measure N2. I would have a hard time measuring how it varies in the R direction. It may not vary very much in the R direction at all, in which case this term would be 0. But in any case, I know that the quantity itself is very small. And so as long as this, if this is a positive number and if this slope is positive, then this adds to the rod climbing effect. If this derivative is a negative number, then this detracts from the rod climbing effect. But since we do see rod climbing, we can say must not detract very much because we see this. We see this. So this, I think, is a very nice demo because it shows that even without solving the problem, we can learn quite a bit from the equation of motion, just from the momentum balance and knowing a few things about the stress. It also demonstrates that these normal stresses do come in these kind of pairs, in these normal stress differences very comfortably. And that's because the Navier-Stokes equation, the momentum balance, only care about normal force differences. They don't care about the absolute values. So starting on Monday, we'll start on the next chapter, which is material functions. And the piece that we haven't talked about yet, I remember I've been making the analogy to ASTM standards, and we've talked about shear flow. But we haven't said with what time function do I move this top plate? Do I move it at a steady rate? Do I move it 0 and then start up something and then stop? Do I move it in an oscillatory fashion? That's all governed by this sigma function in the definition of shear flow. In elongational flow, there's an analogous function, the epsilon dot function and the sigma dot function. These two functions we're going to talk about next and define our version of the ASTM type standard functions. We're going to define standard material functions that are based on standard choices for these functions. And that's what we'll talk about next time. And then this is our ASTM standard procedure. Okay? If you want to poke and prod a material and talk to other rheologists about it, this is how you do it. You choose whether you're going to talk about shear or elongation and which type of elongation. You'll specify the time function. You'll put the material into an instrument that carries out that time function, and you'll measure the stresses. You know now what the stresses look like. In shear flow, there are 3 stress quantities, and in elongation, there are 2. And then you're going to report your results in terms of the material functions that I'm going to define next week. Those material functions are the end of the ASTM sort of standard. And then you can do 2 basic things with these material functions that we're talking about. You can just talk about them. That would be this green box. This is what people in industry do. They measure eta prime, eta double prime, eta star, G prime, G double prime, all these various quantities, and they talk about them. They say, oh, this material is higher or lower than that material. Oh, the function has this shape or that shape. And it's a very useful thing to do. And I'll talk about it, and I'll teach you how to do it. Or you can take those results and think about them and try to use them to find constitutive equations. And that's the other thing that we're going to spend our time on in this class. So that's a little bit of a preview of what we'll talk about next. So we're done. Have a good weekend, and see you Monday. Questions about the exam, please ask on Monday or during office hours.